So after having used geometry to solve a bunch of integrals, the question comes up, and it's a pretty obvious question, is like, what happens, what do we do when we have a function that doesn't lend itself to using the area of a triangle or the area of a rectangle to find the integral, right? So just like we have methods of approximation for derivatives, aka the slope formula, right? We can also approximate integrals in a couple of ways. So let's take a look at our problem. We now have a motorcycle problem instead of a bicycle problem, and we are interested in times 2 to 7. So we want the integral from 2 to 7 of v of t dt. And we're going to approximate. So right away I'm going to make this little squiggly equal sign, which means I'm estimating, right? And if we're going from 2 to 7, we want 2 to 7, right? And notice right away that this area, it's not a nice geometric shape, right? It's the area under a parabola. That's t squared, so definitely a parabola, right? And we don't have a formula for the area under a parabola yet. But what we can do if we're approximating is, well, I can make a bunch of little rectangles underneath this parabola. So notice I don't quite capture all the area. I have these areas, little areas here that are not going to be in my rectangles, but it's pretty close, right? It's like more or less accurate. So this is called a Riemann sum, and the way I do it is just base times height for each rectangle, right? So let's go ahead and label my rectangles. They all have a base of 1, right? Because I cut it up into 5 intervals. And then my heights, well, they're going to depend on the x values. And remember, this is t squared is my function, so it's pretty easy to figure out my heights. My first one's 4. My second one, 3 squared, is 9. My third one, 4 squared, is 16. And then 5 squared, 25. And my last one, 6 squared, is 36. So this is what my work would look like. And for one this simple, you probably do not need to show this step. But if my width was something other than 1, I might, right? And when I add all those up, I get 90. And we're talking about miles. Are we talking about miles per hour? Let's say we're talking about miles here in hours. So 90 miles total. Okay. So this was not the only way to do this, right? So that I can chop it up in a number of ways and make a good estimate a number of ways. For example, what if I considered the same time interval from 2 to 7, but instead of making my rectangles underneath, I'm going to make them kind of poke out above, right? So this is still an estimate of the same thing. However, we now have pretty obviously an overestimate, right? Because I have my rectangles that kind of poke out. We have all these little corners that stick out, right? That are then overestimating the area under the curve. It's still an estimate of the same integral. And that integral is from 2 to 7 of v of t. Still an estimate, so I'm still going to use my squiggly equal sign. But here, well, instead of my height, my bases are all still 1, but instead of my height being 4 for this first one, my first one is 9 right away because it has a height of 3 now at this point. And then from there on, notice we're like one rectangle higher each time as we go through this. So this one's 36 and then 49 here. Right? So it's the same math, but I get a different estimate. And it makes sense that we might want to estimate these things different ways in different situations. So if I want to know how much gas I'm going to use on my trip, it's better that I overestimate my mileage than underestimate it, because if I underestimate it, I might not put enough gas in, right? I think you get 135 miles here. Doing this without a calculator, by the way, so you might want to double check that. Okay, so notice we have two different estimates of the same thing. They're both good. They're both equally valid. When we have two different methods, right, it's useful to give them a name. So these are both called Riemann sums. My first one is a left Riemann sum. My second one is a right Riemann sum. And the difference is just where the endpoints are. So my left Riemann sum uses rectangles, right, with their heights given by the left side of the interval. So what I mean by that is every corner of my rectangle, it touches the function at these points, right? So the left-hand corner of my rectangle is the rectangle that I'm using to find the height. Those are what I'd plug into my x squared to get the height. Whereas our right Riemann sum is the opposite. Meaning my heights are given by the right-hand side of each rectangle. And we also note, right, that one of these is an overestimate, one of these is an underestimate. So my left Riemann sum is an underestimate for increasing functions, and my right Riemann sum is an overestimate. And this is actually opposite if the function were decreasing, and you can draw a little sketch here and maybe figure out what that would look like. So here we have our two ways of cutting our function up into little rectangular pieces to estimate its integral. This, by the way, is how your calculator does it. I'm going to show you how to do that in a future lesson. But it's not the only way, right? And in fact, I can show you a more precise way, and that's going to be our third method. So let's still use that same integral. Oops. So it's going to be the integral from 2 to 7 of v of t dt. Still an approximation, but what if instead of making little rectangles, I made little trapezoids? So see how closely that approximates our area? It's not quite perfect because these are assuming the rate of change is constant, and we know that that's not true of a parabola, but it gets pretty close. It minimizes the over or the underestimate, right? It's actually an average of our Riemann sums. So what this would look like, well, we still have heights of 1 for all of these, but my bases are a little bit harder. So the advantage of this is more precise, but the disadvantage is the math is a little bit harder. It's not super hard though. So remember, our formula for a trapezoidal, or a trapezoid area rather, is just 1/2 times the sum of the bases times the height. Right? That's the formula we're going to use. So this integral would be equal to this. So that's the area of 1, 2, 3, 4, 5 trapezoids. 1, 2, 3, 4, 5. And I did it left to right. I would pause and just make sure you understand how I got all of this. And then here's a little trick to evaluating this. So if my height is the same, I can factor out my height in the 1/2. So I have 1/2 and then times 1. And then times all of that, right? And then I have an easier sum to work with. Okay, so showing your work is a little unwieldy here, but the math isn't super hard. When you evaluate this, and again, check my work, you get 112.5 miles. So notice how it's right between our other two sums that we got. So this is, again, most accurate, most annoying to solve. And this is called a trapezoidal sum, which makes sense given how we got it, right?